name is Voinarovskyi. I'm going to talk about a little bit simple thing in Python that most of us developers just don't use nowadays because we have too many good libraries, we have database drivers, we rarely go into the memory structures and all, and don't really work with binary data nowadays. So it was quite a shock for me that a lot of people in Python world just doesn't know about the struct package, about the new bytes objects in Python 3. They all think that like you can only work with strings and that's enough. So that's why I wanted to talk about something quite low level, but quite simple, like the basics from which you start in C and so on. So for starters, let me introduce myself. So my name is Voinarovskyi, as I said. I'm an open source developer. I'm a member of the libs team. We had Novik before, talking about distributed systems. He's the same member of us on GitHub. Also, my main focus is on I/O Kafka, and I'm also a collaborator in the Kafka Python project. So this work is basically a subsequence of my experience working with Kafka Python's parsers. So I came to a conclusion that people who migrate from Python 2.7 into Python 3 just have this misunderstanding on why was string object made into the bytes object and so forth. And for some reason, several people just don't know about the existence of byte array class and the memory view, what it is and what it can be used for. So those will be the main focus of the talk. Also, I work at an amazing company, Nextiva. So we have big banners over there, over here. We're amazing. If you want a prize, come check out our booth. Hooray, we're an American company. Yay, we have many dollars. So, yeah. So what's on today's menu? The topic will be split into two main parts. First one will be quite simple. I'll explain the data types, how to work with binary data, what are the use cases for those modules. I'll explain a bit about binary I/O and the sockets, and then, sorry, bear with me, we'll just move on to the memory layouts, how they're on C. We'll remember our C class from our university, how structures are formed. Yeah, kinda a big step. Let's see how it goes. So, in the prehistoric times when we still used Python 2.7, we had this kind thing that someone thought was a good idea, that Unicode can be actually casted to string and vice versa. For example, here I create a simple string and cast it to Unicode, and voila, it works. Well, yeah, if your name does not start from Teres, well, if you're Cyrillic, you'll get this nice error over here, and that was a pain of the newbies developers beforehand. Well, this is the microscopic issue of a greater issue that was before Python 3. So nowadays, there's a we have a good distinction. So we have the binary data in the bytes object and the string data in the string object. The bytes object is basically the char array in C. So indexing the array will return actual integers in the scope of from 0 to 255. In the string data, we index not bytes but characters. So the actual first character will return C, though my name's C, like the Cyrillic C, is actually 2 bytes. So we index characters. And the length also returns the number of bytes for byte array data and the number of characters for the string data, though the byte count is actually higher because of the Unicode. So also, this one struck me as a very strange when I started developing on Python 2.7. When we read a file and we opened it in binary mode, strangely nothing happened. Like, it was the same file, it returned the same data, and it was equal. So I was like, why would people need the binary option here? Actually, as it turns out, the logic of file handling in that case turns 100% upside down. You have absolutely different handling of the new lines and so forth. That was one of the problems Python 2 had. In Python 3, it was changed. So now if you open the file in read mode, it will return string data, like the actual string, which we can see, which we can interpret as a character data. On the other hand, if you open a file in the binary mode, we always get the bytes object, which we interpret as typical bytes objects in the range from 0 to 255. So basically, it's an array of integers. And of course, the results for both reads would be not equal. So, we have another two data types. Those come from the byte array was around from Python 2.6, so it's actually a fairly stable thing that we had all along. Just for some reason, it had limited scope of functionality, like the limited use cases. I don't know why. It's a great thing. It has the same interface as string has, so it has the encode methods, but also it's an editable structure, so it can also serve as a list. You can append to the object and you'll get one at the end. You can slice it to do a mem copy. This one's especially useful when you're doing network management and you use byte array as a buffer. You can actually do fair mem copies. Like on C, it will actually do the mem copy, so it's fairly efficient. That's why this one's actually great to use instead of just joining strings together. Also, we have a memory view object. So to explain why a memory view is so great, we'll get onto that on a later time in this topic. So for now, let's say that like someone used Go. Go has this slices object that is actually an ability to say, I have a big string and I want to interact with part of the string without copying it. So the slice just remembers the pointer to the object and the offset position and the length of the bytes we want to work with. Memory views can be used in a similar fashion. Like here, I take the view of the original buffer object. I changed 5 bytes in the memory view using the memory view interface, and the original object actually changes. And this is also a fair mem copy operation on the C level, so it's fairly efficient. To be fair, those 3 data types existed in Python 2.7, but in 2.7 we have a bit of a difference in the API. So the memory views in 2.7 actually return substrings as the indexes, like the str class does. The only object that does not have a change in the interface is byte array, which is why if you have a library that should work on both Python 2.7 and Python 3, byte array is a great object to use as a buffer because it has the same interface on both Python interpreters. If you have TCP memory slicing, parsers, and so on, use byte array, you will not have to use 6 compatibility issues that get on overhead over your program. So that was a basic introduction. Let's go into something more fascinating. So binary data. If you look at data streams, files, and so on, we typically have 2 types of data. The textual data, which can be seen by the eye. You can actually look at it like JSON, YAML, and so forth. And the binary data, which is used in databases. You can look at it, but it will basically look like Darth Vader. You don't know what's actually there. So to get a meaningful information on the binary data, you should parse it, and only then you will be able to understand it. Those are the 2 worlds people live in, and in Python 3 there's a conceptual separation between the 2, like the strings. In IO class you have the text wrappers and the binary IO, and so forth. So for example, let's say you have a C++ team, and they say, okay, we made this dump file of 1 terabyte messages here in a file. Could you please process them? Those are images or something. Could you please process them somehow? And you're like, well, why isn't that something like JSON or anything? But C++ developers actually love to do that. So how should we solve this problem? The dump file would have some simple data structure. For example, in this case, I have an ID, which is an 64-bit integer, a 32-bit integer for the length. We have some CRC, which is unsigned 32-bit integers, a version that is a byte, and the bytes object body, which has the length. Yeah. So. How should we solve this task? For starters, we need to somehow understand those 64 and 32-bit integers. The Python has no notion of variable length integers, like different integer types or anything. We only have the big integer implementation, which is long and goes up as we go. So how do we do that? Structures are your allies. We have a library called struct in the standard library of Python. There are 2 main methods and several others you can read about in the documentation. Basically, we can pack using a format and passing out our values. The format specifies in this case a 64-bit integer, a 32-bit integer, an unsigned 32-bit integer, and a byte. We pack that all together, and we can unpack it using the same format, and we get the same values. So this is what powers the drivers in let's say MySQL, if you have a pure Python driver. And for those who use PyPy, great news. This works freaking awesome, like super. It's faster than C, really. I was astonished just how fast the struct library is on PyPy. Well, for those who remember some basics of C, you kind of understood that the format is basically a description of a structure in C. So the Q is equal to lon, the I is equal to int, I is equal to unsigned int, and B is equal to signed chart. Why is it a great thing? Because in C, if you want to use a structure, you can actually cast the structure to a pointer and just read the bytes of the structure directly without any conversion. That's why it's so damn fast, and C programmers just don't like to do it in any different way, like why JSON is hard. So all the specification you can read in the documentation, what format characters, for what C++ and C types. We have different values like floats. Currently modern in GPUs are the half floats, which are floats of 2 byte characters, 2 bytes, 2-byte floats. Those are kind of modern right now. They were added in the latest Python, so Python 2.7 just doesn't have them, sorry. But of course there are problems with that. So as the integers they have this notion of alignment and size and the big endian, little endian thingy. So if I pack an integer, simple integer on my laptop, it's a little endian system, so the 5 goes before. But if I want to send it into the network, there's a convention that the network packages are encoded using the big integer format. Well, just most of the protocols actually use big integers in the packed version. Well, I don't know, that's written in the structure package. I didn't come up with that. Okay, so maybe I'm wrong, but I found those a lot of times. I see those, so okay. And if you pack a big integer, it will go to the end. So structures, simple structures have the notion of alignment. If you create a structure with a byte and an 32-bit integer, it will actually take 8 bytes on your system, depending on your compiler, depending on your system. That can change. So to have a standard way of expressing that, there's a way to specify a modifier before the format character. In this case, I specified the big endian modifier, and in this case, the size will be a standard size. And integers like the int type in C can actually have different sizes, like it can be a 32 or 64-bit integer depending on the platform. So, and different opcodes have like standard or native sizes. You can read on that in the documentation also. There are several modification characters. So now that we know how to pack simple types and to unpack them, let's try to write something that actually reads from a file. There are several points of efficiency when using buffers and memory management. The first point here is that usually when you read it from a file, you would just use the read command. But the read command actually creates a new bytes object, so it's an allocation in the system. It has some overhead. In our case, we just want to scan the whole file, and we know that each message will have the same length of the header. So we can allocate the buffer once with the size of our needed structure and use the read into command to read exactly into our buffer from the file. This will let us avoid the unneeded allocation each time we want to read another message. Then we will unpack it and proceed with our scanning. Another thing I want to mention here, of course you can avoid this by just passing your buffer size to the buffering option. I just wanted to note that I/O has several wrappers around your streams that you can use. Buffered reader is basically the same that is returned if you pass in a non-zero buffering here. Just wanted to do it a bit more explicitly. When you open files in your Python application without passing the buffering option, it will use a default buffer size. Depending on the system, it's somewhere around 8 kilobytes. If for your use case, like when you're reading a large file, you can specify a bigger buffer, so it will use less syscalls, like 10 megabytes or so. And another thing here that I seek to avoid reading the body part of the message just to be more efficient. What's of interest here is that the buffer reader actually helps me here to avoid a number of syscalls. For example, if I had not wrapped the file into the buffer reader and used the read into directly, I would have a lot of syscalls with actually reading small parts of data, which is inefficient. A syscall is actually a great overhead if you're working on something low level like parsers or readers. Try to avoid that as much as possible. So on this note, I want to have a little off-top. When reading from a socket, the same stance. If you read from a socket, read a lot. Do not read 4 characters. Not to mention that this is just plain invalid code. If you have a socket, you have a receive method on this socket. This operation can actually return 1, 2, 3, and 4 bytes. So there's an error here. You have to actually check the size of the return value. The proper way of writing that would be to read as much as possible to avoid the unnecessary syscall. If data is empty, it means that the socket is disconnected, and feed the data to some parser you created somewhere else. So end of the off-top. Okay, so now we know how to read files. That's great. Now let's talk about something more interesting. Software is built on several things, and in a computer, the buffer is something very essential. Like from the memory reads, from the disk reads, the socket reads, everything has a buffer. You can tweak it, you can change it. Like if you open a socket, you can change the amount of the OS buffer to have a more efficient framing, and so on and so forth. So to make your program more efficient on the wire, buffers are very helpful. But what is a buffer in Python? So Python is a language that is based on quite immutable structures a lot of the time, and only byte array is somehow mutable in this context. Strings are immutable, you can't change a string. So what can I use as a buffer? As it turns out, Python has this notion of bytes-like object, and several APIs can actually actually specifies that you can pass in any byte-like object. For example, the write command on a file. Did you know that you can write a bytes object to a file? You can write an array to a file, and you can actually create a NumPy array like any matrix, n-dimensional, and you can write it to the file. Not that I would recommend doing that, but you can. Why? Because Python has this thing called the buffer protocol, so any object can create an interface for interacting with its internal buffer. Like in the NumPy case, it's the matrix which is used underneath, and the buffer protocol gives you the ability to look at the memory directly without using an intermediate API. And that is what is used here in the file write. Where can it be useful? So in C, on the C level, if you're writing a C extension, that's the essential way of interacting with objects, because it's a common interface. You don't need NumPy sources to compile and get access to the internal data. You can just call a Python function, I mean the C Python API function, and you can receive a structure containing the void pointer to the actual data you want to interact with. Just a note here, the byte-likes object in the terminology of Python is stated as any object that supports a buffer protocol exporter of a C continuous array. So in the buffer protocol, there's a notion of a non-continuous memory where you have several parts spread out in the heap, or if a single chunk should not be read sequentially, but like in the Fortran case where you have columns first rather than rows in your data. So, wow, let's move on. Memory view is an interface that actually works upon this buffer protocol and gives you a Python interface for interacting with the internal buffer. In this case, we create an array, get a memory view on it, and we can see that the view has the shape of the array. In this case, we state that we are viewing a matrix consisting of 4 elements. It's a one-dimensional matrix, and the item type is a 16-bit integer value. The opcodes here are the same as the struct package we mentioned before, so read the documentation for that to understand what type is mapped to this character. If we take the view and make it to list, we'll get the first 2 values specified here. So the slicing is actually working in the format specified above. So memory view does not give you a simple ability of Go slices. It's actually a view of an n-dimensional matrix buffer in the memory, like that. What can also be done through memory views is that you can cast the types. For example, in this case, I create a simple string of 5, cast it to an integer, 32-bit integer, and I get one value 5. But if I cast it to 16-bit integers and say it's a matrix of 2 dimension to 1 dimension, I'll get an n-dimensional list structure when I parse it. So it can be used as some kind of a simple parser for matrices, but NumPy is way better at that. If you really need to parse data, use NumPy or specified data science utilities for that. But if you want to do something simple, this is a great use case. So where are memory views especially useful is where your API does not let you specify the offset and the length of the data you want to interact with directly. Like in the read into case, the API just receives a buffer and reads up to the length of the buffer. So if the buffer is a large one, it will try to read as much data as it can into it. For example, in this case, we create a big buffer. Let's say that this will be written to another file. You just want to interact with it, but you want to read only a part of the file from here into this earlier specified buffer. So you create a memory view on this large one and say, I want to insert into this slice, and then you call read into, and it will populate only 15 bytes, as you can see here. A great use case for memory view too. So yeah, what I mentioned. Let's sum up the first part. Use struct models to pack and unpack simple types. Use binary I/O for interacting with binary files. Proper buffer management will let you have efficient programs, and memory views will let you avoid unnecessary copies of your data. So, going deeper, yeah, into the sand actually. This one's a bit tricky. What I want to state here is, okay, we have a big buffer. Why can't we just take a part in the middle and interact with it? Like, it's simple. In C, I can do it just by casting my pointer to an integer, adding the offset, and just casting back to another object. that will not work for several reasons. One of it is that every object in Python will require you to have a prefix before your object in this memory. So it will have to have the PyObject head, which is actually contains the reference count and type information. Type information is basically your class, if you didn't know that. So there's also a notion of var head that is present in lists, tuples, bytes, etc., etc. It contains a slot for the number of objects in this object. And of course there's the PyGC head. I don't have time to talk about that. So let's move to something more interesting, bytes. How do we store bytes in memory? A great question. Actually, bytes are stored as a single chunk of data. So what comes up from that? There are two rules to memory allocation in Python. First, the object cannot move after its creation to a different address in memory. From that, we cannot reallocate a byte object after it is created. So it's static. Once we created it, we can't change it. The second, the object's length cannot be changed after creation. That's a rule also. So why is that a rule? Is because small objects are allocated in arenas in Python. The arenas are just like small sections, and so if you allocate an object once, probably after that object there will be another one to make the memory compact. So you cannot enlarge an already created object. There is no space, and if you shrink it, you should move it to a different space to avoid memory fragmentation. So you cannot do that either. This is why bytes object cannot be changed, and you cannot like say, okay, I want to use the data part here. It does not have the prefix, nor does it have a byte object at the end. So byte arrays, yeah, this is the C structure. Byte arrays, how are byte arrays different? Of course they are different because it's a writable structure. Writable structure means that we will need to reallocate the internal buffer to a new section of memory. In this case, we will need to have it in a separate heap location. So byte array is actually split into two objects: the internal buffer, which can be reallocated, enlarged, and shrinked, and the header part, which contains PyObject head, the size of the internal buffer. Object alloc is the number of bytes actually allocated in the internal buffer. So when byte array appends an object to the end, it actually overallocates your buffer to be of a bigger size to allow faster appends in the future. And one moment here. If you use a byte array is optimized on slices from both sides, meaning that if you append to a byte array, it will be fast. If you remove from the end, it will be fast. And if you remove from the start, it will be fast also. You can see here that I created a byte array, removed from the end and from the start, and the object size did not change. Why is that? Because it did not reallocate to a different section in the memory. It just moved those two slots. The object bytes is the number of characters actually used. The object start is the pointer No, the object bytes is the pointer to the actual internal buffer, and the object start is the logical pointer to the start of the data. So if you remove from the start, it just moves this object start pointer. It does not slice the data nor reallocate it to another space, at least until your buffer is not 50% unused. Like if you remove more than 50% at the start, it will reallocate your data, but until then it will keep it allocated. This is the reason if when you will have not really good fragmentation of your memory, but it has to be there for efficiency. What I want to say is a great choice if you want, for example, TCP stream, and you want to append to one end and cut off on the start. It will work efficient because it's optimized on slices at the beginning. Let's talk about the buffer protocol. Buffer protocol was implemented in Python 2.7 as a new protocol. Before we had some strange implementations that we'll not be talking about like ever. So it was created in a separate PEP. This PEP is a great example of how to not write PEPs. Why? Because it contains so many improvements that it was not implemented up till now. Like we have Python 3.7, and there's still an issue about upgrading the struct package with the new opcodes provided in this PEP. So if you write a PEP, just say add one thing, do not write a PEP to add 3 or 4 things, because if it's accepted, you can only implement part of it. It's strange. So what it proposed: any object can export a void buffer in C level into a simple C structure on the stack. It can support an n-dimensional n-dimensions, and we provide a memory view as an interface in the Python API to interact with this buffer object. Why? How does it work? So if we have a byte stream, we create a simple structure in C. We create a pointer to the internal buffer, which is over here. We take a reference to the original object, incrementing its reference count. So as long as this buffer is not released, the original object will not deallocate itself because the pointer is upgraded. And of course, we have the length of the original object. Those are the basic ones which help us have a sequential view of the memory. There are a lot of other options that give us the ability to interact in an n-dimensional space and not see continuous arrays where you have different offsets in memory and you have to read the metrics in not sequential order. There are a lot of things here you can read in the documentation. So what was the use case for this? So why was it created? Firstly, it was created as an array interface in NumPy, as far as I'm concerned, and only then was it proposed and accepted in the Python community. So the idea: you're writing a C extension for your application code, and you have like this big pill object with an image, like you have a doctor great image, 1 gigabyte of data, and you want to have a C processor on this data. You will use OpenCV or any other C++ tinny. So how do you access that data if the only thing you have is a Py object? You cannot. The answer is simple. You cannot if you do not have an interface to interact with it. And an alternative would be to take the NumPy package sources, include the header files, take the structure, and get the offset in the structure itself, which is not great because you have to cross-compile with it. This way we can just take a NumPy array, get the buffer, do something without GIL and release the buffer. That was the use case in C. On the Python level, we have a memory view. The memory view is actually more complex than you would want it to be, and it contains a lot of fields. I will skip that for now. Any questions? Yeah, if you're interested, come see me after this. I'll explain, but the memory view is a bit too complex to explain in 3 minutes. Sorry. Yeah. Questions? No?
So because you have these differences in the API between 2.7 and 3 point something, like currently the packages that have to support both, what's the situation? I mean, I guess it's not easy to do something low level and make it work in both cases.
So the packages I explained were there for a very long time. So the structure package was way before 2.7. You can use it. Basically everything I showed here works with minor differences in Python 2.7. If you do not write a cross-compile version of the library, you're okay. Just read the respective documentation. It works with strings the same way as it works with bytes. The only difference would be the memory view part, because in 2.7 that they still had some issues with the memory view, and those will never be fixed. Yeah, sorry.